Good afternoon, everybody, and welcome to the first AEE member webinar for 2020. Just a few housekeeping things before we get started, as always. Just want to let you know that if you do have questions during the course of the presentation, please post those in the questions section of your control panel for GoToWebinar, and all questions will be addressed at the end of the presentation. With regards to copies of the presentation, Mr. Mamani is going to share with me a link that I can share with you all so that you can access a couple of things, and he will explain that during his presentation. Your follow-up email that you'll receive 24 to 48 hours after the end of today's presentation will include for you the usual. You'll have a link to the recording of today's presentation and a link to your certificate of attendance. So if you have anything specific that you need to ask me, you can type that in the question section of your control panel, but make sure that it is directed to me. If you have a chat section, you can do that in there. And also remember the questions for the Q&A session at the end of the webinar to go in there also. So thank you everyone for tuning in today, and I will go ahead and introduce Mr. Ali Mamani. Mr. Ali Mamani will be presenting today, and the topic is Predictive Demand-Side Management Optimization. So Ali Mamani is a head of data analytics research at Prescriptive Data, Rudin Management Company, and an adjunct research scientist at the Data Science Institute of Columbia University. He specializes in multidisciplinary optimization, complex system design, deep structural networks, and cyber-physical systems, with a focus on the following topics: heuristic optimization algorithms, machine learning, deep learning, recurrent neural networks, multi-fidelity modeling and optimization, and uncertainty analysis, and with primary applications in building energy efficiency. Mr. Mamani graduated with his PhD in mechanical engineering. He has authored two book chapters and more than 30 international journal conference articles. He is a professional member of AEE, IEEE, ASME, and a senior member of AIAA, and a selected member of the AIAA Multidisciplinary Design Optimization Technical Committee. He serves as a reviewer for 15 international journals in the areas of design, computing, and energy. In addition, Mr. Mamani is also involved in organizing and chairing technical sessions on emerging topics in the ASME IDETC and the ASME PEC conferences. So thank you, Mr. Mamani, for being with us today. Thank you to all of those tuned in. I am going to pass control over to Mr. Mamani at this time.
Thank you so much, Sharon, for the introduction. Let me... Now you can see my screen, yes?
Yes, we can see your screen.
And you had, okay. So thank you, Sharon, for the introduction, and good afternoon, everybody, and thanks for joining us today. My presentation today is on using battery storage technology in demand-side management. Today's presentation is prepared based on my research that is recently published in Applied Energy Journal. And later today or tomorrow, Sharon and I will share with you today's slide and published paper. And first, I have to acknowledge National Science Foundation and Department of Energy to fully support this research effort. Again, I am head of core research and data science team with a company called Prescriptive Data, and adjunct research scientist at Columbia University. First let's talk about, if I can move my... Yes. Can you see my presentation?
No, we're looking at the intro screen right now.
What about now?
Nope, not right now. Let me just see.
I think you are the presenter now.
No, we're just looking at the intro screen. Let me just see if I can. There we go. Now we're back to your screen.
Yes.
There we go.
So let's talk about prescriptive data before going through the today's presentation. As you can see in the screen, at PD, prescriptive data, we offer building operating system and cutting-edge building application. Our building OS that is called Nantum OS is a reliable, robust, and secure platform that enables the implementation of data-driven energy conservative measures designed by other companies, research centers, universities, and also Nantum OS enables the implementation of other non-energy related applications that are designed to use building data and provide services to tenants. In addition to providing the robust AI platform for other companies, we also use Nantum platform to offer a set of data-driven applications, including a fully automated, optimized startup and shutdown app, which is designed to start and shut down the building as a whole or in floor-by-floor basis. To doing that, we consider outdoor, indoor conditions and real-time human occupancy data reading. We also offer an advanced space utilization app that is using machine learning and Wi-Fi scrapping technology to count number of occupants and estimate the percentage of occupant seats in office spaces. We have ML-based anomaly detection app that is using the cutting-edge ML algorithm to find the anomaly in building data, anomaly behavior in the building data. And also we have OpenADR-based demand response software, which enables the communication between the utility and clients during demand response events. We also have a machine learning-based measure and verification application that is designed based on IPMVP protocol to estimate or approximate the energy saving of different technology offered by us or other companies or other research centers. And top of that, we also have a set of HVAC system optimization application that helps us reduce the energy consumption and greenhouse gas emission of buildings. Now, let me go back to today's presentation. Today's presentation is about demand side management and how we can use battery storage in demand side management. Here you can see my the outline of this presentation. I'll start with motivation and motivation behind of this research effort, and I'll go through the background, formulation, research review of this research, and I will talk about the test bed that we prepared at Columbia University to implement our developed framework in the real world application, and then I'll show you the end result and how we made battery cost effective for the demand side management. By exploring the capacity and typical, can you hear me?
Yes, sorry, I can hear you. Can in the audience? Sorry, I've just now noticed that we have a few questions in here. Saying a couple of people saying there is no sound. So could you please type in the question section and let me know if you have sound? That's a question for the audience. Okay, we're good. They're all coming in, yes. So that must have been earlier before we actually. Perfect. Thank you, everyone. I'm sorry to interrupt you. You can continue.
Okay. About the motivation. By exploring the capacity and typical summer load of different ISOs in United States, we understood that more than 20% of the total installed electricity capacity in US is dedicated to satisfy peak load, which only happens 5% of the time. This exploration, this study showed us that the peak generation capacity to meet this peak demand is economically inefficient. On the other hand, we know that the peak reduction will significantly reduce the stress on the electricity grid, which helps the environmental and overall reduce greenhouse gas emissions. So we understood that the peak reduction is significantly important for environments and has lots of economical advantages. So there are different technologies available in both demand side, building side, for example, and supply side, the generation side, to provide a balance between demand and supply during peak hours. We should be very careful here about the balance. When we are talking about the balance between demand and supply during peak hours, it doesn't mean that we can get the full capacity of the supplier. Definitely no. The balance means suppliers should not be environmentally inefficient. So we should use the capacity of the generation side up to the point that the generation of the electricity is economically and environmentally efficient. That is very important for us. But what sector has the highest impact on demand side? Well, it is very clear for us that commercial and residential buildings have the highest impact on the overall peak demand. And between commercial and residential building, because the prediction of the peak load and peak demand is much easier in commercial building, it's much easier for us also to manage the peak reduction in commercial building compared to the residential building. So in our research, we mostly focus on commercial building, and we are focusing on finding a way to reduce the peak load in commercial buildings. Now let me go through the definition of demand side management and what is the exact meaning of demand side management. Demand side management includes all the practices that can be followed by end use customers, building engineers, building owners, and in residential side or in commercial side, to change the normal consumption pattern in response to changes in the price of electricity or some incentives that are designed by utilities. So utilities, they know that at what time the generation of the electricity is not efficient or is not environmentally efficient. So they define these time beforehand or 24 hours ahead or 5 hours ahead of the event by changing the price of electricity or by providing some incentives. Customers can respond to the changes in the cost of electricity by reducing the energy through different practices. The most common one is load shifting, in which consumers move electricity consumption from one time period to another. For example, pre-cooling in commercial building, or postponing the laundry time to midnight in residential building. These are the example of load shifting that we can practice in response to the demand response event or to change the consumption to off-peak time. Another technique is peak shaving. In peak shaving, customer reduces consumption of energy for a very short period of time, maybe 1 hour or 2 hours, to avoid the peak. But this off-peak, on-peak time might be 6 hours. This is either possible by changing the behavior of the building, for example, shutting off a couple of elevators or reducing the level of light in the building, or increasing the set point temperature in summer days. or we can rely on battery to help us shaving the peak without changing our daily behavior. So we can use battery. We don't need to change our behavior, and again, we can get to the goal of shaving the peak. And the last technique is valley filling, or increasing demand at off-peak time and smoothing the overall load. For example, charging the electricity vehicles during the night, or for example, again, charging the battery storage on off-peak time when the cost of electricity is much lower. As you can see here, the demand side management is not only one practice. It's a combination of different practices that we have to follow, and all the objective is smoothing the load profile and reducing the overall peak demand and help the environment. There are different demand side management technologies available, and mostly all of them actually initiated by utilities. The first technology is direct control technology, or direct control system. In this technology, utility remotely, most of the utilities, they do this, they remotely control the customer registered appliances, only registered appliances. For example, they increase the set point temperature through a smart thermostat. Con does this in New York City, for example. Con provides us in the residential side, residential buildings mostly, with a smart thermostat for free. So they can control, manage the overall peak during the peak summer periods. And in return, they give tenants free theater tickets. So it's like a encouragement for them to be in the demand response program. At the same time, Con provides free thermostat, free smart thermostat, and they can control the load. But we can understand this technique doesn't work for the commercial building. It's mostly designed for residential building or very small offices. So they design another technique, they call it the load limiter technique. In the load limiter technique, which is mostly designed for commercial buildings with building management system and building automation system, in this technique, customer or building engineers or building owner agrees to react to demand response by limiting the total electricity consumption. So we need to have a platform to communicate, to have a communication between utility and building, mostly BMS. So OpenADR here provides a communication. It's like an open source protocol, provides a communication platform that enables the secure communication line between virtual top nodes, which is utility and ISOs, and virtual end nodes, which would be BMS in buildings. In this case, the virtual top node provides start and end time of the demand response event, and the amount of load each building needs to be contribute in reduction of the peak. So then the building have different practices. They follow the different practices to answer to the request from the utility and reduce the overall peak load. The last technology, which is getting very common these days, mostly in New York and California, is time of use tariff structure. So in this technology, demand electricity cost is set to be very, very high at peak load time, and it would be very, very low at off-peak time. This technique encourages customers to engage in load management practices. So we had the time of use tariff structure before, but the difference between the off-peak time, the difference in the cost in the off-peak time and peak time now is getting more pronounced. So that makes profitable to follow some practices to manage excuse me, to manage the load and shift it to off-peak time. Here in bottom part, I put the example of time of use tariff offered by Con Ed for commercial buildings in New York City. As you can see, the demand cost is almost 2 times during the peak hours, comparing to that in off-peak time. What about the battery storage? And during the past few years, electricity storage system or battery storage system have significantly impacted the applicability of demand-side management techniques. So basically, the advanced battery storage that we have right now help us to be more involved in demand-side management technologies. So, and mostly in commercial buildings, what we can see these days that we have Tesla Powerwall for residential buildings also. So we have very advanced and much cheaper battery storage, and now with a relatively very high rate of discharge and charging of the battery, we are able to use the battery storage in demand-side management. At the same time, utilities companies define different time of use tariff structure that make these new battery technology much more cost effective. So when we use the battery, we are taking advantage of time of use tariff structure. We charge the battery storage during off-peak time, and when the electricity is much cheaper. And then during the peak hours, when the electricity is expensive, we discharge the battery to reduce the peak load. The higher the difference between the cost of electricity in off-peak and on-peak time makes the battery storage more profitable. But we have to consider something here. Usage of battery leads us to use more energy. So we are reducing the peak load, but at the end, we are using more energy because of the efficiency of converting AC to DC or efficiency that we have inside the battery. So I will explain it in battery formulation. There are different researchers from different companies and different research centers and universities that they explored storage-based demand-side management in commercial and residential buildings. And most of them use model predictive control algorithms, MPC, to formulate the battery dispatch strategy with the objective of minimizing the peak load. But the researcher for that I'm presenting here today is not only optimizing the battery strategy to be used in demand-side management. At the same time, we are considering the interior space temperature optimization. So we concurrently optimize the battery dispatch strategy and interior space set point temperature to reduce the peak load more than required to offset the storage cost, battery cost, and provide an overall cost profit to building owners. So this is there are a lot of efforts in this area. People are combining battery storage with other different techniques. In this study, we consider all techniques of pre-cooling and or changing the set point temperature to control the demand, and battery storage dispatch technology to control the peak. Well, the primary objective of this research is to design a comprehensive framework that is designed mostly on top of particle flow optimization algorithm to minimize grid loads and electricity costs. Again, a reduction of the peak doesn't mean reduction of electricity costs. we have to consider a right tariff structure, because if we use the battery storage, eventually we use more energy. So we have to use the battery in a right way to reduce the peak and eventually reducing the cost of electricity. In our formulation, we also consider a system payback time, a very accurate cost model for the battery and for the financing of the battery. And at the same time, because we are optimizing the interior space temperature, we have a constraint of thermal comfort. We have to satisfy occupancy thermal comfort. But what would be the first thing? The first step in our develop framework is understanding and finding the optimal capacity of the battery storage. So if you want to perform demand side management using battery storage, first we should know the exact size of the battery we need to buy. Yes. So we call this step a passive demand side management, because we are using the historical electricity consumption data and historical weather data to find the optimal size of the battery. Two important modules that we use in this optimization problem are monthly tariff model, which is we use a Connet time of use tariff model, and battery storage model. A tariff model reflects the cost of electricity during peak time and off-peak time. And battery storage module models the behavior of the battery storage in the real time. So when we are talking about the passive optimization, but every minute, every 15 minutes, we have to have the behavior of the battery storage, mostly the state of charge of the battery, to be considered in our formulation. So we need to have high fidelity battery storage model also. If I go to formulation details, the optimization is defined as a mixed integer nonlinear programming problem. And the continuous variables in this optimization problem are monthly demand limits. So assume that we have 12 months. So we have off-peak, partial peak, and on-peak limits in different months. So we have almost 30 continuous variables. And we have the size of battery storage as our integer variable. So we need to formulate the problem as a mixed integer nonlinear program problem, which is a combination of integer and continuous variable. And we do have a battery cost model and accurate tariff structure model that can calculate the energy demand cost with highest level of fidelity. So it has to be very, very close to the reality. So because of that, we develop a tariff model separately. We compare our results with the real billing mechanism that we got from Connet, and then when we got to the certain level of accuracy, we use that model in our calculation, in our formulation. As you can see in the formulation of passive demand side management, or finding the optimal size of the battery storage, we also need to have a very, very accurate battery storage model. So we are talking about every 15 minutes, every 5 minutes, we have to talk with the model and get a response from the model in about this state of the charge. So we developed a mathematical model of our battery. So the battery was already developed. The physical battery was already developed at Columbia University, but we wanted to have a very accurate model that we want to be used in our formulation to calculate the capacity that we need in our test bed. So we modeled the battery storage with the highest fidelity that was possible for us. In this model, we considered all important properties, including round-trip efficiency of the battery, which is the round-trip DC to storage to DC energy efficiency of the battery. We consider the efficiency of the DC AC inverter. We consider battery depth of discharge, which refers to how much energy is cycled into and out of the battery on one given cycle. And we also consider the cycle life and maximum battery lifespan, which is used to calculate the monthly cost of the battery, because we wanted to have a very accurate cost model for our battery. And the most important one was the maximum rate of charge and discharge, which for our battery was 1C. This is very important because we cannot charge the battery in 1 second, for example. Yes, the technology is it's improved a lot, but again, at this time, we cannot pass the limitation in our formulation. We wanted something that a model that the result of that would be very, very similar, almost similar to the real world battery that people designed before at Columbia University. So obviously, we also designed a control module for our battery that covers 3 different modes: charging mode, discharging mode, and the neutral mode, which obviously are functions of all the properties that I mentioned. The round-trip efficiency, inverter efficiency, depth of discharge, and the rate of charge. So the output of this mode function is the state of the charge of battery at every 5-minute interval. So we can call the battery, get the state of the charge, state of the charge. But you can see that the most of these parameters are changing during the time. Because of that, we consider the battery degradation model. So in parallel to the of modeling the battery, we have another model for modeling the degradation of the battery to understand what would happen. For example, if you use the battery after 2 years, what would be if the state of the charge would be different, or for example, lifespan would be different. To consider these kind of scenarios, we formulate the battery degradation and make the battery financing model and our battery model much more accurate. And you can see we consider different factors, including calendar charging, number of charging, number of discharging, and depth of discharge in our formulation. And you can find the details of our battery degradation formula in our published IEEE paper. So we publish these battery degradation model separately in another journal because it was getting very dense, and we didn't want to consider it in one single publication. And yes, now, so the first step was finding the optimal size of the battery and using the battery model and battery degradation model and the electricity cost model, which is from Conet, time of use theory from Conet. And after finding the optimal size of the battery and installing the battery in our site, we need to have a real-time demand-side management algorithm that helps us using the battery in real time and real-world application. So the problem is now it's changed. It's not finding the size of the battery. We know the size. We want to use it. The scheduling, the problem is how to use it in the right way. So to answer this objective, we developed another algorithm. We call it a real-time DSM, or real-time demand-side management. As I mentioned, we want to optimize the dispatch strategy of the battery. And at the same time, we also want to optimize the interior system temperature in different zones of the office building. Therefore, the objective of real-time DSM is reducing the electricity cost, and at the same time, we have to satisfy the human comfort. And our two or design variables are scheduling of the battery or dispatch strategy of the battery, and interior space temperature set point. So the procedure of the real-time DSM starts with predicting the demand profile using weather forecast data. So the input data, we start the real-time DSM starts from 24 hours ahead. We have a weather forecast data available. We use our ML algorithm to predict the demand profile of our building, and then the optimizer finds the optimal demand limit for dispatch strategy of the battery, and finding the first result for the optimal set point strategy, optimal set point of the interior space temperature for that target date. Definitely, the weather forecast is not accurate. Definitely, our machine learning is not accurate. So the system is like a real-time learner. So over the time, the model is updating itself. The set point temperatures are updating. But because, for example, the building was empty at the Columbia University, so we had time to update the set point temperature at the same time updating the dispatch strategy of the battery that you're working with. And yes, so if you look at the formulation in more detail, the formulation of the real-time optimization, real-time demand-side management optimization, we can see that the real-time demand-side management is defined as a hierarchical optimization problem. So there are, it is two-level optimization. So the interior space temperature is optimized at higher level, with having the real-time thermal comfort as a constraint. So the higher level optimizer is trying to get to the optimize the interior space temperature, and is considering the thermal comfort as a constraint. The current that we were using actually 55 standard to understand the level of comfort, and not passing the class A and class C in thermal comfort. And the battery dispatch strategy is optimized in a lower level, with considering the operational constraint. So there are a lot of constraints for battery storage. So you cannot, for example, increase the rate of charge at more than 1 C, or we cannot overcharge the battery. So there are a lot of passing the depth of discharge or charge. So there are a lot of constraints for the operational part of the battery. So the lower level optimization is considering how to optimize, how to schedule the usage of the battery, considering the battery storage constraint, operational constraint. And the overall objective of hierarchical optimization problem is minimizing the electricity cost. So we want to make the battery cost effective. We want to show that using the current time of use tariff designed by Con and using the battery storage that's with the real cost associated with that, we can use the battery to reduce the peak. At the same time, we can show that a battery can be cost effective also. So again, the accurate battery or electric storage model and accurate tariff model are used, which was very important for our formulation. Here we can see that if we remove the battery storage part, it means that if we remove the lower level optimization part, the problem would be very similar to a pre-cooling optimization problem. Means that how we can play with the interior space temperature set point and reduce the peak load. So this is a combination of pre-cooling, the traditional pre-cooling optimization problem to reduce the peak load, and using battery storage to help us to reduce the peak load even more. So after we were done with the formulation of our framework, we were looking for a testbed to test our developed software framework, real testbed. To do that, we considered part of a building at Columbia University that is sub-metered directly, and we could see the changes in the electricity consumption. At the same time, we were able to change the interior system temperature and show and see the impact on the total electricity consumption. In the table that I showed in this slide, you can see the equipment that were available in the testbed and the energy consumption of each, and during the occupied hours and during unoccupied hours. So to consider this testbed as a representative of office buildings, first we compared the load profile and the load factor of our small testbed office with other typical office buildings in New York City during the winter time and during the summertime. And we found that based on the profile and load factor, we got to the point that our testbed can represent the big office building. So, and we also we also did the comparison on the end usage of electricity because we had the desegregated electricity consumption in our test bed. So we also compared the desegregated electricity consumption, the electricity consumption associated with lighting, equipment, small equipment, ventilation, cooling, and fans, and compare desegregated data proportion of the consumption to real big office buildings in New York City or the typical office buildings in the US. So yes, the purpose of all of these comparison was to understand whether our test bed is a good representative of typical office building and finding out if the developed software. So if our test bed is a good representative, we can say that our developed software can be used in other typical office building, and the result would result with some level of error can be obtained in other building as well. So we perform a lot of tests that is listed in my paper, and we share with you guys. And we understood that yes, the test bed is good enough. So then next step was finding the right size of the battery storage for our small office at Columbia University. So we implemented our passive DSM software on historical data of our test bed and to find the optimal size of the battery storage. So we went through all the procedure, we ran our algorithm in on historical data, and we find the right battery storage size. We also found optimal demand limits, or that are used for dispatch strategy of the battery storage, or scheduling of the usage of battery storage in for different summer and winter months. And after finding the optimal size of the storage, we wanted to implement the real our battery and our finding in the real-time demand side management. So we did it. This slide shows the impact of battery storage in reducing the peak load in 1 week of implementation. And in this figure, the y-axis in the left represents the grid load, and then the y-axis in the right side shows the state of change of state of a charge of the battery storage. So yes, the electricity consumption is much lower than big office buildings that we mostly have in New York City. But as we already studied, it can be a good example. It could be a test bed of to show that yes, it is possible to use battery storage even in big office buildings. And you can see the battery is discharged to reduce the peak load in light gray areas, and it is charged during the off-peak time during the day, every day. You can see the algorithm also is very smart. It is smart enough to avoid the weekend load, because the peak load is during the weekend is much lower than weekdays, and using of the battery only increase the energy cost. Only because if you use the battery during the weekend and peak load is not the monthly peak load is not reduced, so you only increase the consumption of energy, which increases the cost of energy at the end. So the algorithm was smart enough to avoid weekends or not working days, and to have much more saving. And again, let's go to the slide that shows the variation of the optimal interior space temperature and the comfort estimated through predicted percentage of dissatisfied PPD from ASHRAE 55. So here you can see the weighted percentage of dissatisfaction, and because we wanted to consider the impact of occupancy on PPD, so we modified the formulation to be weighted based on the occupancy, and 1 minus of that would help us to have the maximum value of 100. So if the 1 minus WPPD is 100%, doesn't mean that the building is, for example, the interior space temperature is in comfort. It means that no one in the building is dissatisfied about the interior space temperature. So in top figure, you can see the set point temperature if you would follow the ASHRAE 55, and in the bottom figure you can see the control point that is controlling the interior space temperature, optimize the interior space temperature profile to reduce peak load. But this is not the end result for the pre-cooling, because in this scenario the algorithm is trying to optimize the interior space temperature profile in such a way that battery storage would be much more cost effective. So it's like, so if we run the algorithm without battery storage, we did that. We got different results. So, but the saving, if we consider both of them together, the saving is much more, and we can reduce the peak load and help the environment much more. And this slide shows the significant reduction in peak load in summer month, and as you can see, we got to up to 30% reduction in the peak load, which was significant for us, and it obviously helps the generation side a lot, and helps the environment and helps us to reduce the greenhouse gas emission. And this bar chart shows the result of developed software in dollar figure, so in different months, and we also compared their results if we wouldn't, for example, use battery and interior space temperature together. So the first one is if we wouldn't have any action. The second bar shows if you only if we had only pre-cooling in the system. The third bar shows battery only, and the last bar is PDSMO, which is considering battery and temperature profile optimization to reduce the peak. And again, you can see developed software saved the electricity cost up to $700 per year. So we also consider separately the impact of we consider separately the cost of battery storage in our formulation. So on top of that, we could save $700. $700 is not that much, but for the building that size, it's significant. And but if you look at this reduction in the peak, we got to the reduction of 30%. So without spending any money at 1 year, we can reduce the peak by 30%. And this was amazing result for us. At the same time, we also study the impact of the interior space optimizer to see if we are satisfied comfort class A and comfort class C, and we saw that in more than 95% of the operational hours, we were below those predefined lives by actually 55. And so we can say that we developed a software that not only provides saving, it reduced the peak significantly, and at the same time, we are satisfying the human comfort. It's not great. So if you, for example, follow this one specific temperature, make the building super cold or super warm, yes, the comfort would be better. We satisfy the comfort, but we didn't overcool or over warm the building. So in conclusion, we developed a demand-side manager framework that concurrently optimizes the thermal storage, scheduling, and interior space temperature. It is designed based on time of use tariff structure. If we didn't have the time of use tariff structure, it was impossible to use the battery and make it cost effective. So we have to have the good tariff structure to make this profitable. So we show that we could save the electricity consumption. We can reduce the electricity consumption, the cost of electricity consumption by 10.7%, which was enough to pay for the monthly payment of the equipment cost. And we reduced the peak load significantly by 26%, which I guess the number which should be 30%. I put the wrong number here. And let's go through questions. I'm done. Thank you. Sure.
Thank you. Okay, so we do have a small number of questions, and I'm sure we will have a few more now that people have been listening in and know that you're ready for the questions. So a couple of people are asking about copies of the slides and the recording of the webinar. I will be sharing an email in the next 24 to 48 hours, just letting you guys know where to find the recording, a link to your certificate of attendance, and also details on how to get the presentation. So now, topical specific questions for you. Any harmonics issues by installing the battery system, especially due to the switching in inverter?
For the installation part, because we have a very good support from other research group at Columbia University, they designed and they implemented the battery. So we were not involved in the real installation of the battery in that test bed. So, but I can direct you to those people to help you if you have some questions.
Okay, so then the next one, what is the capital cost of this technology and what would be the typical payback in implementing this in a typical commercial building? It seems that it says amortization schedule might be quite long.
The real-time optimizer. The first question, we didn't scale it all. We didn't consider if we go to real building, what would be the benefit and the cost? Because at the time that we were doing this research, we couldn't have access to the real-time consumption and inside temperature of the building, real building, huge building. So we didn't do that. What was the second question?
It was, I'm sorry, it says, what is the typical cost and what would be the typical payback?
Yeah, we didn't explore that. So there was another question, I guess.
Okay. You mentioned that the transportation sector contributes 0.2% of the peak demand. Do you think that this will change with the increase of the electrification of the transportation sector? And wouldn't that create new peak demand periods?
Absolutely right. So if we go through, if we have more electric vehicles, so the profile of the ISO demand profile will be changed significantly, and this is the research topic. A lot of researchers are working on this. The demand would be shift from on-peak time to off-peak time, and this is a new challenge for utilities to how to manage this. So in Texas and California, they did this research, and they said they found that I guess in the next 50 years, because there are a lot of electric vehicles, they are charging the cars during the night. So maybe we have a shift of electricity usage and peak from morning to night. So definitely, you're right.
Okay, in sizing your batteries for your application, did you take into consideration the battery degradation? And if you did, how was it treated?
Oh yes, I explained in one of the slides. We in the initial study we didn't consider the battery degradation, and then we understood that it has a huge impact. So again, we went back through our formulation, and we developed a battery degradation model, and then it was getting we were involved a lot, and then we saw that this is an opportunity for us to have another publication about that, and then we published in another paper. One of the paper that I put in the first slide, the IEEE paper, is mostly about degradation model.
Okay, a couple more people asking for copies of the presentation. Let me just get a little bit further down here. What software platform is the optimization algorithm implemented on during the test?
Oh yeah, we use particle swarm optimization. The programming language is MATLAB, and we use PDSMO, is the open source particle swarm optimization algorithm developed by our group when I was doing my PhD, and it is publicly available as a MATLAB package in MATLAB website. It's a mixed integer nonlinear programming algorithm.
Okay. What is the effect of using renewable energy for charging the batteries instead of charging through the grid?
Oh, that changed the problem a lot. We didn't study that, but definitely the formulation would be different. We have to consider that separately. Yes, the grid would be negative during that time, and sometimes it would be helpful, but the formulation would be much more complicated, I guess.
Okay, just we are at 3 o'clock right now. There are several more questions, and I do have a couple more slides that I need to run through right here. So I'm just going to take a couple more questions, if that's okay with you, Mr. Mamani, and
Yes,
then
yes.
we will close for the day. And if you have follow-up questions, I will share Mr. Mamani's email address with you in the follow-up email, and you'll be able to direct those to him personally. So the next question. Two-tier optimization used for comfort and cost of energy. What was the main objective? Cost versus comfort?
Yes and no. We wanted to have if we wanted to consider both of the optimization in one single formula, we couldn't have it in the real time. So to make the procedure much faster, we wanted to have it's like a parallel computing in the formulation, but at the same time, we have two optimizers. They were fighting together with each other. So the formulation helped us to reduce the complexity of the problem and make it happen to have the result in the real time. So we reduced the computational time significantly by formulating that. In future, maybe if there is no need, if you have advanced computing power, maybe that formulation would be one single optimizer managing everything. But we tried that, we couldn't get to the point that we can use that for one single optimizer and get to the result in the real time.
Okay, we will make this the last question. How replicable can this be on other more complex commercial buildings, and how big of an influence can the local weather play in the applicability of this application?
Both of them are very challenging questions. The first one, we cannot use battery storage based on the fire safety law in New York City. We cannot use battery storage in New York City, and we have different law in Arizona and California, but we were based in New York City. We are waiting for getting this permission and then use it to see the impact. And the second question, weather forecast has a significant impact. As you see, so we run the model, and the result was, for example, if we were running the model at midnight, the result was changing a lot. And from the result that we were getting, for example, at 6 a.m., because of the weather forecast was changing significantly, dramatically. And the accuracy of the weather forecast has a huge impact. Improving the accuracy of the weather forecast would have a huge impact on the accuracy of the set point optimization, dispatch strategy optimization of the battery storage.
Thank you very much, Mr. Mamani. So I'm just going to run over to my presentation and just run through a couple more slides. But thank you, everyone, for tuning in today. Just a couple of reminders from us here at AEE. We do have all of our certification options online. Both live and online options are accessible at the website that you see right there on your screen. Please go see what we have on offer, and we hope to see many of you taking up some of our training. And just to give you a little bit of a heads up, these are the webinars that are currently planned going forward. Most of these people are confirmed, and we are also working with a few more to build out the program for the remainder of the year. So that just gives you a quick heads up of what else is ahead for the coming months. And our next member webinar takes place next week on Thursday with Mr. Jeff Stoltz, and he will be talking about energy storytelling. So please tune in with us again then. We do have 4 events coming up this year. We hope to see many of you visit us at one or more of these locations. And finally, we will be at the AHR Expo in Orlando next month. We will be at booth 770. So if you are attending and would like to stop by, we would love to see you. Please stop by the booth and say hello. So thank you, Mr. Mamani, for tuning in today. Thank you to everybody else for being here. And I am going to go ahead and close out the webinar. Bye for now, everyone.
Thank you. Bye.